Welcome to SnowEx Liquid Solutions training module, Liquid Anti-Icing Post-Treatments and Performance Results. If pre-treating with liquids has become a standard best management practice, post-treating with liquids is now at the cutting edge of snow and ice control. In this module, we will explore what liquid anti-icing post-treating is and why it can be a beneficial approach. We will also look at best management practices for when, where, and how to execute this strategy. And finally, we will review the results of well-documented field studies of post-treating and their cost benefits. The objective of anti-icing post-treatments is to preserve or maintain existing ice-free conditions and extend bond prevention. This strategy is most commonly executed after plowing and utilizes a slightly higher application rate than pre-treating due to the amount of moisture present, somewhere in the ballpark of 20 to 60 gallons per acre. Used appropriately, post-treating with liquids is an effective and efficient alternative to salting. It can maintain or achieve safer levels of service faster than traditional de-icing approaches, using less salt, causing less damage to property and the environment, and reducing overhead costs. There are several points in the order of operations when anti-icing can be an appropriate strategy: before, during, or after a storm. Since there is some discrepancy in the way during or post-storm direct liquid applications, or DLA, are referred to in the industry, before we start, I'd like to clarify our definition. Anti-icing is commonly defined as a pre-storm operation to prevent snow and ice from bonding to the surface. Consequently, during or post-storm DLA is often referred to as de-icing, which is not a completely accurate representation. There are two possible objectives for DLA post-treating. One is to de-ice or break the bonds, such as would be used for black ice or hard pack. These strategies are further discussed in the training module on de-icing. The second objective for during or post-storm DLA is to maintain and extend existing anti-ice conditions, even with the presence of accumulation on the surface. In this module, we follow the precedent established by Clearroads in its recent studies on application rates and define anti-icing first and foremost by its objective to prevent the bond, regardless of the timing of the operation. There are three types of DLA anti-icing post-treatment approaches. The first is a reapplication of brine as a maintenance measure to extend anti-ice conditions achieved by pre-treating the surface earlier. This is typically executed following plowing measures in place of salting, when residual accumulation has not formed a strong bond with the pavement. The second is an initial application of brine, also executed in place of salting when plowing measures result in surface conditions that are predominantly clear of compacted accumulation. This is to further inhibit ice from bonding to the pavement. The third is the direct application of brine to the surface of a light accumulation of snow in place of plowing to remove a minimal amount of unbonded accumulation, typically less than an inch. There are four primary factors impacting DLA post-treating strategy decisions. The first is pavement temperature, which can vary by up to 20 degrees from the air temperature. The pavement surface is where snow and ice control is taking place. The second is the type of de-icer being used and the application rate required to achieve goals. The performance of a chemical under specific conditions is predictable and repeatable. If desired results are not achieved, it is not the de-icer's fault. The likelihood is that the assessment of other variables may have been in error. De-icer performance and pavement temperature are variables that can be determined by science. Next is moisture type, the amount present on the surface, and the anticipated rate of continued accumulation during ongoing operations. And lastly is cycle time, or the length of time until you will cycle back to service that site again. When using during storm DLA, this becomes especially important when the storm is ongoing. Assessing the impact of the last two variables requires keen observation and professional judgment and is an art that only experience working with these tools can provide. Other factors impacting decisions include the amount of sunlight on surfaces and traffic. When post-treating with DLA, dilution and refreeze become especially critical to material strategy and application rate decisions. Liquid de-icers work faster, but because they start as liquids, they dilute and refreeze faster too. Assessing the various factors that impact dilution will dictate if post-treating with DLA is the right choice in a given situation and determine the appropriate application rate and cycle time to prevent refreeze. This skill, or art, is acquired and perfected from experience executing these strategies over time and under varying conditions. The phase diagram shown here for salt brine is a scientific tool to help understand the freeze point and melting capacity of salt brine at different temperatures and concentrations. Illustrated here by the red star, the freeze point of salt brine at 50% dilution is 18 degrees Fahrenheit, below which at that concentration it refreezes. At pavement temperatures above that at 50% dilution, the brine still retains melting capacity. The art involved with DLA is judging how fast a specific de-icer will dilute given the existing moisture on a particular surface and the rate of accumulation at the current pavement temperature. Clear Roads, a consortium of 34 state DOTs in partnership with university programs and application experts, did an extensive field study of during storm DLA in 2010. The participating agencies are indicated by the dots on this map and show areas where this strategy proved highly effective. The best management practice guidelines for during storm DLA that resulted recommend a 1.5 to 2 hour cycle time until the surface is resurfaced by plowing and/or a DLA reapplication. The most effective application rates varied from 20 to 60 gallons per acre, or 0.5 to 1.5 gallons per thousand square feet, somewhat higher than for pre-treating due to the moisture present during or after a storm on the surface. In 2013, the Michigan municipalities of Farmington Hills, Novi, and Wixom collaborated to further test the results of the Clear Road study in their region. We appreciate their sharing some of their results using salt brine. For the purpose of this study, most of these were standalone applications without plowing. As a rule, clearing snow is recommended prior to using a chemical strategy. The picture seen here is of a parking lot immediately after a post-treatment of 55 gallons per lane mile with a pavement temperature of 28 degrees Fahrenheit and an estimated 3/4 of an inch of snow. And this is the following morning with no traffic on the surface overnight. The gray box is used to illustrate the difference in cost between DLA and traditional salting. All such estimates are based on $70 per ton of salt and 8 cents a gallon for salt brine, and do not represent the actual data relative to the application shown. Here DLA results were achieved using the equivalent of 126 pounds of salt per lane mile versus 350 pounds for traditional salting, and at an estimated cost of $4.40 compared to $12.25, a 64% reduction in cost. This shows a lightly trafficked residential street immediately prior to a post-treatment of 45 gallons a lane mile with a pavement temperature of 16 degrees Fahrenheit. And this is what it looked like only 25 minutes later. Again, the gray box shows the comparative use of salt to achieve these results at 103 pounds for the DLA versus 350 pounds for traditional salting, and at a cost of $3.60 versus $12.25. Black and wet in 25 minutes at 70% less cost. For this example on a cul-de-sac, the pavement temperature is 11 degrees Fahrenheit, so an enhanced brine blend consisting of 80% salt brine and 20% snow melt was used. The pictures show the conditions prior to a post-treatment of 50 gallons per lane mile and 3 hours later. Note the residual snow in the shaded area where the sun has not impacted pavement temperature. When post-treating, a blast at a higher application rate in the shaded area would have addressed that variable. In this last illustration, both sides of the street have been plowed first. The pavement temperature is 22 degrees Fahrenheit. On the left, plowing is followed by salting with pre-wet salt at 350 pounds per lane mile. On the right, plowing is followed by a DLA of salt brine at 60 gallons per lane mile. The results shown here 30 minutes later are relatively similar, but the difference is in the amount of salt used and the cost. 357 pounds of salt at $12.50 per lane mile on the left, versus 138 pounds of salt at a cost of $4.83 on the right, a 62% reduction in cost with a comparable result. Here we compare the costs of taking an anti-icing versus traditional de-icing approach on a 1-acre parking lot. For this example, we utilize higher application rates for the DLA pre- and post-treatments at 35 and 60 gallons respectively. The rates for de-icing come from a 2015 Snow Magazine State of Salt report, where 60% of contractors surveyed indicated using salt application rates of between 1 to 2,000 pounds per acre. Note the reduction in both the amount of salt used and the cost. A 78% savings from utilizing a preventative anti-icing approach. Input your own application rates using this example to determine your potential cost benefit. In a similar example, for 1,000 square feet of sidewalk, we are using commonly reported application rates for both anti-icing and de-icing. The anti-icing approach utilized 5.3 pounds of salt at a cost of 20 cents versus 25 pounds of ice melt at a cost of $4. A 79% reduction in salt and a 95% reduction in cost. The substantially higher cost of ice melt is only one reason sidewalks are an ideal place to take a direct liquid approach. To summarize, best management practices for anti-icing post-treatments with salt brine include the following parameters. Accumulation has not bonded to the pavement. Pavement temperatures typically fall above 20 degrees Fahrenheit. Application rates vary between 20 to 60 gallons per acre. The rate of ongoing accumulation is less than 1 inch per hour, and the cycle time is under 2 hours, or there is less than an inch of additional accumulation expected. Post-treating with liquids for the purpose of anti-icing, when used appropriately, reduces labor, equipment, and material costs, and can achieve equal or better levels of service faster than by using the traditional de-icing approach. Thank you for your interest in liquids. For additional information on different operations that utilize liquids, see the modules on liquid anti-icing pretreatments and de-icing with pre-wet or DLA.